Anyways, first I'd like to thank Professor Novak for inviting me, and thank you all for coming. So I wrote this textbook. It's 10 years old, but it's selling better than ever because quantum computing is selling better than ever. And it's in the hype, it's in the front page of the New York Times. It's on every single technical web page. There's always excitement about it. And it's a good thing. Anyways, I'm passing around this book. It's a very readable book. It's made for an intelligent high school student. Just pass it around and you'll see. So this is what we're going to talk about. So, I promise you we won't go beyond an hour. My attention deficit disorder kicks in about 40 minutes, and then it's a little bit hazy. Okay, so, can you read this? Or should we shut the light or something? Or it's fine, I don't mind. If you can read it, can you read it? I'll read it with you. What is all the buzz about quantum computers? We will explain a little quantum mechanics, and in order to know about quantum computers, we're going to have to do a little bit of quantum mechanics, some quantum computing. How will it change our lives, and how it will not change our lives? Is the hype about quantum computers justified? Okay, and there is a lot of hype. So we have to, like I said, it's everywhere and anywhere. So here's the outline of the talk. We're going to talk about some quantum mechanics, some quantum computing. We're going to actually do an algorithm in quantum, within a quantum computer. It's the simplest algorithm possible. We're going to talk about what happens when they do make a quantum computer. If they did, so then we can talk about it now. But the post-quantum world and the hype. Okay, so let's start with this. So we need to have two ideas about quantum mechanics to get into them. Not hard, just mind-bending, but not hard. Okay? So so the first thing is called the double slit experiment, and we'll go through that. Richard Feynman, he's a famous physicist, is discussing this experiment. He waxed lyrically. Okay? We choose to examine, this is from page 1 of his lectures on physics. So this is like his introduction to all of quantum physics is based on this thing. We choose to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. Okay? So people think about quantum mechanics, they think it's mysterious and strange. It is, just because of this strange thing. We cannot make the mystery go away by explaining how it works. We will just tell you how it works. Okay? And this is the world's greatest physicist saying that. He's not going to make it go away. Okay? And the idea is as follows. This is called the double slit experiment. You have light going here. You have a sheet of metal with two little slits. Okay? And what happens is, think of light as a wave. So the waves come here and the waves come here. And what happens is the waves cancel each other out. And instead of having two strong light forces right over here and over here, right directly across, what you have is this, sometimes it's very bright, sometimes it's very dark. Sometimes it's very bright, sometimes it's very dark. What's going on is that the waves are canceling each other out. Okay? The waves from this top slit are canceling out the waves from the other slit, and sometimes they're both on top of each other, and so they make it bright. And that's what you have here. Makes sense? I mean, this is at least 150 years old, 100 years old, no, 150 years old. And so, by the way, if you only have one slit, if you close this off, then the light comes straight across like this, and it's going to be bright over here, and less bright over here, and less bright over there. It's going to be like this. Bright in the center, less bright anyplace else. But when you have two slits, you have bright, unbright, bright, unbright, bright, unbright. You have this interference pattern. You have things canceling each other out. Okay. Good. Light can be thought of as a wave, and waves from each slit cancel each other out. The interference leads to light and dark patches. So it's light and it's dark. Physicists can do this experiment with one photon at a time. So photons are little light atoms. Okay? And physicists have perfected just releasing one atom at a time. Okay? If this is done many times, most of the photons will land in the light regions. None of the photons will land in the dark regions. Watch. Okay? This is what, forget about this for a second, this is what you expect. if you're doing it one photon at a time, many different times, one photon, one photon, one photon, some will get through here, some will get through here, and go over there. So you would expect this to happen. If you're saying that light is an atom, it's no longer a wave, then you would expect this to happen like bullets, if you were shooting bullets. Okay? This is what you would expect to happen. But what really happens is this. Again, you have the light-dark patches. Now that's shocking. I'll explain to you why. Because if you're going to tell me this light is like a wave, so you have waves canceling each other out, very, very nice. But if you tell me I'm sending one photon out at a time, question, who is he canceling out with? Why is there an interference pattern? Who is he canceling out with? Okay, that's the big question. Okay? If there's only one photon let go at a time, what does the single photon interfere with? If you tell me you let two photons at a time, so fine, somehow they're interfering with each other and you're getting that interference. But if you're letting only one out at a time, how could there be interference? Answer. Okay, and this is the shocking thing. The photon splits into two and interferes with itself. Okay? It does not go through either this slit or that slit. It goes through both slits at one time. The single photon goes through both slits at one time. Rather than saying it has a position, it's here or there, position, I'm here, I'm there, okay? It has what's called a superposition, many different places at one time, or two places or many places at one time. Here's a way to look at it. The photon comes here, it goes through, it splits up, it goes through slit A and slit B at the same time, and it cancels each other out. Okay. In quantum mechanics, many properties, not just position, but something we'll talk about later, spin, energy, momentum, do not have a single value. They're not single things. They're not, oh, it's spinning this way, it's not spinning this way. It spins both ways at the same time. It's not has positive energy and negative energy. It has both things at the same time. Now, as weird as that sounds, it's true. Do not have a single value. Rather, they have many values. They are in a superposition. Not just where is the particle? Is it here or is it here? But what values does the particle have? It has this value and it has that value at the same time. They are all seen in a position. They are, when they, oh, now here's another thing. So they're in a superposition. Now, you've never seen a superposition, okay? Unless you drink a lot of tequila, you've never seen a superposition. Everybody you see is one, okay? Okay, you knock yourself on a hammer with your head, maybe you'll see two, but you've never seen it in a position. But before it is measured, it has many values. So when you look at things regularly, okay, it's in a position. But before you look at it, what we learn is that quantum mechanics says things are in many positions at one time. Okay, key idea. Before measurement of the object, a property does not have a definite value. It has many values. You are permitted to scoff at this in disbelief. Yell out, balderdash. I cleaned that up. Okay? You don't have to believe this. Most people do not believe this. Most people, even at the end of this talk, will not believe this. Okay, they think, oh, the physicists are making a little mistake. Okay, Einstein did not believe it either.
Why is it that you see it in a position? If it was in...
That's a good question. In other words, he's asking, he says, look, if the world is really in a superposition, why is it that when we look at things, we only see it in a position? I have no idea. Neither does anybody else. Okay? Neither did Einstein. Okay, it's true anyways, even if Einstein didn't. Okay, Einstein didn't believe it, he just didn't like it. He believed it, he just didn't like it. Anyways, it's true. Okay, now, one of the things, what I said was, if a human being looks at it, it collapses to a position. So one of the things we're going to have to do with our computer is we're going to have to make sure the computer isn't, when it's in a superposition, we're going to want things in a superposition. I'll explain to you why. We want to keep it isolated from everything else. Okay? So we're going to kind of have it, this picture is a little silly because we're not going to have the human being inside the computer, but we're going to have the computer isolated to make sure that humans don't see it or care for it. or find out what values it is. Again, because the minute the second a human being looks at a quantum superposition, it collapses to a position, okay? And all the mystery of quantum mechanics is gone. We're back in the classical world, okay? So not interesting. To keep the superposition, the quantum system and the quantum computer must be kept isolated, so it cannot be measured. Okay, great. So that's one idea, the superposition. And again, that's the main mystery, the main central idea. We will use it, every slide in this today. Okay, next. The other idea is something called entanglement. I'll explain to you what that is. Okay, so these little particles, they have spin. These little particles, they have spin. Whatever that means, they spin a certain way. You can think of them as spinning. But they spin in different directions. They're not like a basketball that spins one way and not the other way. They spin in many different ways at one time. So here's a typical little particle, and you can think of this as the direction. It could be spinning this way, it could be spinning that way. Okay, we have to talk about that. Okay. Now, you can tell which way it's spinning as follows. You can take a source and you can spit out little particles, one at a time, an array of particles. And you can put magnets here. And what's going to happen is some of the particles are going to spin down. What that means is this negative side of the magnet is pulling it in some sense. Some of them are going to spin up, and some of them are not going to be spinning. Okay? And we can control which direction we're looking at by manipulating these magnets, but it's not the point. The point is these little particles do have spin, and we can detect their spin with these magnets. Great. Now, next. Take a particle that's not spinning. Okay? Take some, there's lots of different types of particles. Take a particle that's not spinning. Okay? These particles split. They break apart. Okay? And if this one's spinning this way, then this one has to spin that way. Let me just back up a second. There's something called conservation of energy. What does that mean? That means the amount of energy doesn't change. Whatever you're doing, there's no change. There's a concept of conservation of momentum. If you play pool, you know about conservation of momentum. If you shoot a ball, the white ball, and it's going this direction, it's going to hit a lot of other balls that are going to move in the same direction or different directions, but the sum of all the movements is going to be the same. That's called conservation of momentum. Guess what? There's something called conservation of spin. What that means is the amount of spin in a system doesn't change. So, watch this. If this has no spin, and you split it into two particles, and this one has positive spin, then automatically this one has to have negative spin. Because you've got to keep the spin in the world equal. Okay? Same thing here. If this one spins, and this one is in the negative direction, then this has to be in the positive direction. Okay? Now, the amazing thing is, this is what's called entanglement, is if these particles are very far away from each other, okay, still, that one has to be positive, that one has to be negative, or that one has to be negative, that one has to be positive. Okay? And when I say very far away, I mean across the universe. They have to remain. Now, next. Now let's bring in superposition. I told you, things don't just spin. They spin both ways. They don't just spin this way or this way, they spin both ways at the same time. You cannot wrap your mind around that. You can't wrap your mind around it because you can't accept it, which is fine. It's not acceptable. But it's a fact. Okay, great.
So why is one positive and one's negative if they're both spinning?
Great. So what happens is as follows. You take a particle, you split it in half. Okay? You split it in half. You don't look at it. Close your eyes. Don't look at it. Okay? Send this particle to New Jersey. Send that particle to Florida. Okay? Don't look at it. Put them in a box and don't look at them. Now, when you put them in a box and no one's looking at them, which way are they spinning? Answer, they're spinning both ways at the same time. Okay? Again, They're spinning. I told you, things which you do not look at are doing superposition. Great. Now, let's say this one was Florida or that one was Florida?
No, it was New Jersey.
It was in New Jersey. Let's say you go to New Jersey, you open the box. Now when you open the box, it's no longer doing a superposition thing, right? Because you're a human being, it claps. Which way does it collapse? Positive or negative? It's one of these two. I don't know. It's random. It's random which way it collapses. But here's the trick. The instance that you open this and it's spinning this way, automatically you know this one is spinning the other way. If you open the box and it's spinning this way, automatically in Florida, this one's spinning the other way. That's called entanglement. Things are entangled throughout space-time. They're entangled even though they're millions of miles away. The universe has to keep them straight like that. Okay? Now, let's just go through something a little bit more classical. Let's say I take a dollar bill and I rip the dollar bill in half. Okay? And I put, you close your eyes, I put one side of the dollar bill in one box and one side of the dollar bill in the other box. Right? And I close the box and I send one box to New Jersey and one box to Florida. Okay? Now, the guy in New Jersey opens the box. He's going to find one of those two sides. Right? So he's going to open the box and he's going to see, oh, it's the left side. What does he instantaneously know is in the other box? That the right side's in the other box, right? Okay. That's similar but totally different. Similar but totally different than this.
That's a lack of knowledge.
Say again?
That's a lack of knowledge.
That's a lack of knowledge. I did not know what was in the box. I opened the box. I saw what was in the box. And then I saw what was over there. Great. Quantum mechanics has nothing to do with lack of knowledge. Quantum mechanics has something to do with the world. Okay? It says as follows. Before I open this box with the spinning particles, it is in both things at the same time. It is spinning both directions at the same time. When I open the box, there's a statistical probability of spinning to the positively or negatively, one or the other. The second I open it, automatically, not do I find out what's here, not only does it find out what's here, but also the other side collapses instantaneously. What I do in New Jersey affects what happens in Florida instantaneously. This is one of the strange things of quantum mechanics. This is one of the things that people don't like, but it's a fact. Okay? But a fancy way of saying it is that it's non-local. The universe is non-local. What you do here affects, or the measurements you do here affects the measurements you'll do in other places. Okay?
What if it doesn't split equally? Is that like a thing? Does that happen?
No.
Why does it always split?
It's,
Meaning, let's say one gets 75% of the energy, then it was.
No. Particles either spin or don't spin. They either spin positively, they spin, so they have integer spins or fractional spins, but they have set things. A nuon is going to split into a this and a that.
And the first particle is spinning both directions or what?
No, this I'm just showing you what spin is. There could be
The original particle. Which
sorry. The original particle is not spin, has no spin. That's the whole point. The original particle has no spin, so the total spin of the system is zero, which means if this one's spinning positively, it must be the other one must spin negatively. If this one's spinning negatively, the other one must be spinning positively. We have to keep that total thing zero. Go.
Has this been directly observed or?
Yes, 1,000,000 times. Okay, it's a famous thing called Bell's theorem, but yes, it's incontrovertible.
So my understanding is that they found the opposite particle, but
Right? No, they can do it. Now, anyways, incontrovertible. Go.
So the original particle, is it spinning? It's not spinning?
It's
or
not spinning. We know of certain types of particles that spin. We know of certain particles that spin this way. We know of certain particles that spin. This one is not spinning.
Just a particular particle.
All right. And we can put all these particles into that measuring device, right here, and they'll always go like this. Okay? And well, one second. So let's do this as an experiment. Instead of having one source and particles coming out between two magnets, we're going to have a source here, and it's going to split into two parts. Okay? And it's going to go here, and it's going to go here. Guess what? If it spins this way and not this way, this one, then automatically, this is kind of like a measurement. We're measuring it. We want to see what it is. It goes this way. Automatically, this is going to go this way, even if it's 1,000,000 miles away. Okay. Einstein didn't believe it and called this spooky action at a distance. He didn't like this.
Is it possible for this one to start spinning the other way, and then the
Right,
that
no,
almost
it will be random. In other words, if you do this 1,000,000 times, half of them will come up, and half
the
of them
only
will come
fact
down.
is that the other side will be the
Correct,
opposite.
the other side will be the opposite. And again, this is 5 feet apart, but if you do this millions of miles apart, it still works.
How do we establish that we didn't know that it wasn't always spinning that way in the beginning?
It's called Bell's theorem, and it can be proven. It's a fancy Bell's theorem, Bell's inequality. Go, sorry.
Why doesn't this work on a dollar bill? Put a dollar bill in a box where you have a machine that breaks it apart randomly, puts each half in 2 different boxes. Why isn't that the same thing? Why does it only work on particles?
Because with the dollar bill, it's one thing, okay? And it goes there, and it goes there, and we just don't know what it is. Here, it's not one thing, it's 2 things. Now, I agree, I can't go into it to prove it, but Bell's theorem proves that it doesn't work like that. Go.
When you say we have the particle in the box, right, we're not looking at it,
Right.
it's really spinning in both directions.
Yes,
But as soon as we look at it,
yeah,
it's spinning one direction.
right.
When we look at it, is it still spinning both in one direction? And the only reason why you're saying it's spinning in one direction, do we understand it? Or does it physically stop spinning?
No,
in
it's
both directions?
physically stops spinning in both directions, it spins only in
As
one
soon,
direction.
as soon as we look at it.
The set, not even less than that. It could be, we'll talk about it, it could be that, there's a heat, through heat you can measure it this way as opposed to that way. Yes, the second you look at it.
So what's...
Or the
what's
second it
connection?
becomes in, so there are some people who argue and say it's not, some people say it's human consciousness, because human consciousness has never observed anything in a superposition, okay? I suspect animals also have never, if your cat or dog ever saw something in a superposition, he would freak out.
So it's like the superposition is hiding from us,
Exactly, the universe is hiding from us.
right?
You don't have to believe it, it's true anyway.
Can a spinning particle split, or is only non-spinning ones?
Splitting particles can split too. So
Spinning.
Right. So this one can split. It can split into 2 particles that have half the spin, but the amount of spin that is here has to remain the same.
There's no limit to how many times they can split.
Right.
And the same thing is true for its children splitting, things like that. They also have the opposites.
This is physics, but a particle can split into 0 and the same direction, or it can split into 3 things, 2 of them in one direction and 1 in the other direction, something like that. But the sum of the spins have to go. Anyways, we have to get to the computer part. So we are finished with quantum mechanics. We know 2 things: superposition and entanglement. Now we do a little bit of quantum computing. So let's talk about classical. Classical, you have bits. Bits are true and bits are false. False or true. You have a switch on, you have a switch off. You have electricity going through a wire or electricity not going through a wire. Whatever architecture you use in your computers, that's a bit. Yes or no. Quantum computers are much more interesting, because not only could you have 0, 1, you could have a superposition of 0, 1, and 1. You can be in many different on and off at the same time, and this is the power of quantum computing. Okay, so instead of things being on and off, we have many.
So it's no longer a limitation.
No, quantum mechanics is not a limitation.
I'm saying-
You people who live in the classical world, you're limited.
Right.
You have
I'm
to-
saying- No, I'm saying that's what quantum computers,
Right.
it transcends that limitation.
Exactly.
It's like another
Exactly.
word.
Stop thinking of 0s and 1s. Move on.
But it would be balanced for every part of it that's on the.
No, hold on. A bit is either 0 or 1, on or off, switch on or off, okay? electricity flowing or not flowing through a transistor, a metal ring magnetized one way or another way, etc. You can all figure out over that. A qubit is set up like this. It's in a superposition, okay? So C0 is a complex number, you know, with the imaginary eye. C1 is a complex number. C0 tells you the chances that after measuring the qubit, it will be found in state 0. And C1 tells you the chance that it will be found in C1. So I've been avoiding this whole thing. Question, when you open the box, will it be spinning positively or negatively? Which one is it? Okay? And the answer is, there are probabilities on these things. Okay? And the probabilities are described mathematically with these complex numbers. Okay? So we can make up a particle that most of the time will spin positively, but a few of the times it'll spin negatively. We can make up a particle that'll do this or do that, whatever. These complex numbers are going to describe how these things look. C0 tells you the chances that after measuring it, the qubit will be found at 0. C1 tells you the chances that after you measure it, it will be found at 1.
Why complex?
Great question. I have no freaking idea. Okay, neither does anyone else. Okay, but just to add to your thing, why is it that everything you measure in this world, the temperature, the speed of things, are always real numbers? Why not complex numbers? Time is always real numbers. Why not complex numbers?
Well, you're trying to simulate the probability in real time, right? You're trying to get a statistical probability.
Right.
So
So he's asking a damn good question. He says like this: if you want probabilities is a real number between 0 and 1. So why do you need these complex numbers? Read this paper. I'll talk about it later, but it'll make you feel good about it. Okay, but I'm not taking away the mystery, but the world works with complex numbers. The fact that we see things in only real numbers is a limitation of those. Okay, great. So that deals with 1 qubit. Question, what about 2 qubits? Okay, well, when I look at 1 qubit, I can look at 1 qubit, it will either be 0 or 1. Great. Let's say I have a box with 2 qubits. I open up the box. What could I possibly see? Well, it's going to be, there's 2 qubits in there. It's going to be both 0, both 1, 1 0 and 1 1, 1 1 and 1 0. I have 2 qubits. It's got to be one of those 4 possibilities. Great. So here are the 4 possibilities of what I can see, of what I will see. So I need complex numbers to describe those 4 possibilities. The chances of me seeing them both in 0, I'm going to call that complex number C00. The chances of being 0 and 1, the chances of being 1 and 0, the chances of both being 1. The point is, if I have 2 qubits, I need 4 numbers to describe those 2 qubits. Okay, great. For a system with n qubits, let's say you have n qubits. I have a box with n qubits inside. They're all 0s and 1s at the same time before I open it. I open it, okay? How many possible ways can I see those n qubits? Well, there are only going to be n bits, right? If I have n bits, how many possible ways are there? If I had n light switches don't exist anymore. Yeah. Okay, it would be 2 to the n possible light switches. There would be 2 to the n possible ways. 0, 0, 0, but it's together. Okay. To describe n bits, you need n bits. If I want to tell you, here's 5 switches. The first one's on, the second one's off, the third one's on, the fourth one's off, the fifth one. I can describe it with 5 zeros and 1s. But to describe n qubits, you need 2 to the n complex numbers. This is the hard problem of making quantum computers, because you need exponential amount of complex numbers to describe your things. Okay, every modern computer works with at least 64 bits. Imagine a 64 qubit quantum computer. That would demand 64, 2 to the 64, thousands, millions, billions, trillions, something. My daughter knows the names. Okay? That's, no computer in the world can hold that many things. What I'm trying to show you is that no classical computer can simulate a quantum computer. You might say, look, I don't know all these things about it. You have complex numbers? I know how to implement complex numbers. You have zeros and ones, addition, I can do that on my computer also. So why can't I do this? Answer, because to describe such a computer would demand an immense amount of things. Can't be done by a regular computer. Now this is not mine. This exponential growth was one of the ideas that got Feynman, that physicist, interested in making quantum computers. This is in the early 1980s. He said like this, Feynman said, if you want to mimic quantum systems, you better have a quantum computer to do it. He said like this, he wasn't interested in computers. He was old school, 1940, built an atom bomb, et cetera, et cetera. But he wanted to know about physics, and he wanted computers to mimic them. But he was having a hard time, because if he would have something like 18 different systems that could be here or there, okay, he would have 2 to the 18 possible complex numbers. Too complicated for a regular computer. So he said, you know what, we better get something else. We better start making quantum computers to do that. And he was one of the first people to come up with this. Okay, great. So all this says the states. I'm just talking about the states. What does a quantum computer manipulate? I know what a regular computer manipulates. A regular computer manipulates bits. So what does a quantum computer manipulate? Answer, qubits. Great. But now I want to know how it works. How does a quantum computer work? Okay, so let's go back to a regular computer. A regular computer manipulates by logical gates. Ands, ors. This computer over here has a bunch of logical gates. Ands, ors, ands, things like that. They're put together in such a way to let electricity go through, bits go through, come and go. Okay, that's nice. Great. We put them together like this, and we make such circuits. Okay, we have the input coming in, and these are nots, nands, ors, dors, not, or, and we have outputs coming out, and we build computers like this. Great. Quantum computers. That's great. That's just a review of your architecture class. Now let's talk about quantum computers. In a quantum computer, qubits are manipulated by quantum gates. And I'll show you a little bit about that. A quantum program is going to be a composition of quantum gates. Just like a classical program is a combination of ands and ors and things like that, so too a quantum computer is going to be a composition of quantum gates. It's going to look something like this. Okay? Basically, your inputs are here, zeros and ones, whatever, and they're going to come out, and here, these are devices called, this is a symbol for measuring. Okay? And this is the main idea of all quantum computing. You figure things out in regular, because that's the way you know things. You set up your computer, and then what these things, the H's do, and we'll go through this a little bit, what these H's do is they put them in superposition. And they do many things at one time. And then it goes across doing all types of weird things, and then at the end, we have to measure them to get that. So, position, superposition, back to position. Okay? Because the output has to be a regular output. You have to be able to measure things nicely. Okay?
Is there more energy expended? The cost in terms of?
Even less.
Even less?
Because all quantum computing is reversible, no energy whatsoever.
Oh,
You'll see why. Okay, quantum computer dynamics. Usually we are going to start by putting qubits in a superposition. We start off with qubits regular in a position. We put them in a superposition. Then we're going to manipulate them with quantum gates. At the end, we measure them. That was the three-step process. Classical position, superposition, measuring. At the end, we measure them. The reason why it is hard to make a quantum computer is that it's hard to make sure that we are not measuring the qubits and they can stay in a superposition. That middle stage where we keep everything in a superposition, we better make sure that no human being is looking at it or measuring it in some way. Okay? So we have to keep it isolated. We have to keep it in below freezing temperatures. We have to make sure that it's behind a steel wall, make sure that nothing can possibly measure it. Okay, Now, you can actually go tonight and log on to IBM Q, okay? And this is IBM lets you program a quantum computer with 5 qubits, okay? And what you do is, you can take your gates and put them up and set them up a certain way, and then you say, simulate, which means, oh, 5 qubits? I can deal with 5 qubits. My computer can deal with 5 qubits. Why? Because 5 qubits needs 2 to the 5 exponential is 32 complex numbers. My computer can deal with 32 complex numbers. Not hard at all. Okay? So you can actually press simulate and it will run. It will run it on a classical computer. But more interesting, you can press the word run and IBM will let you, they have a quantum computer that has 5 qubits and see how it runs. Okay?
Does it run differently?
No, it doesn't. Okay? It doesn't. IBM was very proud about 10 summers ago. I'll explain to you later when we talk about factoring numbers. But this got people alive. This is just a way of getting people excited about quantum computers. It's not, you can't do anything. You can't do anything interesting with just 5 bits. You can't do anything interesting with just 32 numbers, whatever. But it's a nice.
Going through the logic gates, the classic logic gates, take the same amount of time as going through like the quantum logic gates.
Yes. Same thing. But
Are they also built with like like quantum logic gates are built with it?
no,
Noise?
logic is no good because it's not quantum. I'll explain to you why. It's not logic. Quantum gates are all reversible. Whatever I put in, I have to be able to get out I have to get out the input from what I get in the input. So think of the AND gate, right?
Right.
Let's say you have 2 things going in, and you get an AND, and there's a 1 there, and the output is a 1. What do you know about the input?
They were both
That both
positive.
inputs were 1. But let's say it's a 0. The output's a 0. What do you know about the input?
You don't know.
You don't know. So then an AND gate is not a legitimate quantum gate, because you have to be able to reverse things. Just okay, so let's talk about an algorithm that you can run on it. Okay, it's a stupid algorithm. Okay, it's a stupid problem, but it's the simplest thing, and you'll see it's the shocking thing that it does. Okay, Deutsch, it's called Deutsch's algorithm. It's named after a guy named David Deutsch. He deals with a function f that inputs and outputs a bit. You have one function that takes a bit in and a bit out. Okay, and he asks the following question. The problem asks whether or not the function is constant. What does that mean? Look, there are 2 possible inputs to the function. 0 and 1, right? Takes a bit, it goes from bit to bit. 0 and 1, okay? So, question, is it constant? That means f of 0 is equal to f of 1. It means whether you put in a 0 or you put in a 1, you both get the same output. The output is constant, it doesn't change. Okay? Or, is it balanced? What does that mean? That means if your input is 0, then you're going to get a different input, you're going to get a different output than if your input's 1. Okay, now this is not hard because there are only 4 types of functions that take inputs from 1 to 0. Let's go through it. Ready? There are 4 functions that can take inputs 0 to 0, 1 and output 0, 1. Let's go through the 4 functions. 0 goes to 0, 1 goes to 1. Right? That's one function. What's another function? 0 goes to 1, 1 goes to 0. That's another function. Okay, both of those are balanced. Okay, the outputs are different. Different inputs, different outputs. Sure, it's not important. Okay, the other 2 functions are constant. Let's see. Both go to 0. F of 0 is equal to 0. F of 1 is equal to 0. There's a constant. They both go to 0. Okay, and the other thing is constant at 1. F of 0 is equal to 1. F of 1 is equal to 1. They both go to 1. Okay, so those are the 4 functions. Now I ask the following question. Question. I'm giving the function as a black box. It's a box. I don't know. I have a box, and I plug in inputs, and I get out outputs. I don't know which of the 4 boxes it is. Question. How do I find out is it constant or balanced? Okay. Now let's think like regular computer scientists. How would you do this as a regular computer scientist? You have a box in front of you. You can put in bits. You get outputs. You want to know is it constant or balanced. What do?
That's both.
Test both. Test both. What do? Plug in 0, get an output. Plug in 1, get an output. And then what do you see? You see, are they equal or are they not equal? Are the two outputs equal or not? You do two function evaluations, right? Very good. Classically, this demands two function evaluations. You have your box, you put in two functions evaluations. Okay, let's just go through it a little bit more clearly. You start off, you have no information. You plug in 0, okay? And if you get f of 0 is equal to 0, then you plug in 1. You do another function evaluation. If you see that both are 0, it's a constant function. If you see that f of 0 is 0, and then you plug in 1, and you get f of 1 is 1, then you see, oh, f of 0 is 0, f of 1 is 1, it's balanced. But it could be balanced this way. F of 0 is equal to 1, f of 1 is equal to 0. These are the four possible functions. And again, 2 are constant, 2 are balanced. But you need to do two function evaluations. Great. With a quantum computer, this problem can be solved with one function evaluation. So again, a classical computer, you need to run that box twice. With a quantum computer, you can do it once. That's a speed up. It's a baby speed up, 2 rather than 1, 1 rather than 2, but it's an important thing. Question, what do you put, how do you run it once?
Split the atom,
Say again?
split the qubit.
Exactly, but what you put into the qubit, what do you put in the qubit?
Oh.
What do you put into the box?
Either one.
Not either one.
Oh, you put in a qubit.
You put in a superposition of both 0 and 1 at the same time. Okay? That's kind of what it does. Okay? It's a little bit more complicated than that, but that's kind of what it does. Okay? I'm not getting into it that much. Don't want to get into it, but basically, here's your black box. You put it in both, and you measure, and you put in a superposition of both inputs, and you measure it, and you get out. Go.
We're only gonna get one result when we measure.
That's why these other things are a little bit more complicated. But yes, so you have to put, you need to control, whatever. Read that paper. Okay. Okay. So this is a baby quantum algorithm, but you got the intuition of it. Instead of doing it at 0 or at 1, you do it at 0 and 1 at the same time. Okay. There's two other quantum algorithms that I want to talk about. One is called Grover's algorithm. Okay. It deals with finding a particular element from a set of n elements. It's called finding a pin finding a needle in a haystack. How do you find a needle in a haystack?
Burn the haystack.
Violence. Okay. How do you find a needle in a haystack? Very simple.
Sexy genius.
Pick up this. Say, oh, that's a piece of hay. 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 Until you find the needle. Right? Okay. So you have to do that if you have n pieces of hay in front of you, or n minus 1 pieces of hay. You have to do that n times. With a quantum computer, classically, this demands looking at n objects. If you want to find a needle in the haystack, you might have to look at n pieces of hay. Okay? A quantum computer demands evaluating square root of n objects. Okay, not n, but square root of n. That's a tremendous speed up. Okay, great. Most quantum algorithms use this Grover's algorithm. Came out in 1995. Okay, great. More important, this is called Shor's algorithm. Peter Shor. Shor's factoring algorithm factors a whole number in a short amount of time. Take a number, factor it. That means find out what it's made out of. This time, in other words, we know how to multiply. Take this number, multiply them together. That's easy. Factoring is a little bit harder. Okay? There is no known algorithm that does this with a classical computer. By a short amount of time, I mean polynomial, but we're not getting into that. There is no known algorithm, classical algorithm, that can factor numbers in polynomial time. This was described in 1994 by Peter Shor. This will destroy RSA. Okay? RSA is the way computers communicate with each other secretly. Okay? And when a quantum computer is built, when they have a quantum computer is built, then RSA will be useless. And there are those people who believe that the NSA, it's the Okay, this is going to be on YouTube, so I'm going to be arrested tomorrow. The NSA has a quantum computer in their basement, and they're already breaking everybody's emails already. I don't know. Okay, let me just go through a little bit about what this is all about. Factoring. Take two numbers, giant numbers like that. It's very easy to multiply them and get the result. Okay, a third grader can multiply two numbers and get them. But going the other way is very, very hard. Given a number 381871637, try to tell me what this, and I can tell you this number consists of two primes multiplied into each other. Okay, so they can only be factored in one way. Tell me what the factors are. Okay, it's very hard. It takes a long time. We can try by dividing divide 2 into it. It's an odd number, it won't go. Divide 3 into it. I don't think 3 would go into it either. 4 won't either, 5, maybe 6. No, 5 won't go into it. Go through certain numbers and try to find it. It takes a long time to do that. You have to try a lot of possibilities. Okay, that's a lot of work. And the answer is 5,000, this times this is equal to this. Okay? Since factoring a large number is hard, it is the basis of all internet security. This is what RSA is all about. This is the way it works. I just want to show you how to do it. You want to communicate with Amazon. Alice wants to communicate with Amazon. Amazon wants to know what your credit card number is. Give me your credit card. Sometimes that works. Okay, so what Amazon does is it takes two large numbers and it keeps them hidden. No one knows it. And by large, I mean a couple of hundred digits. A couple of hundred digits. Amazon has these two large numbers. But they don't send out these two numbers they keep hidden. What they do is they multiply them and they do this. They take this giant number and they send this giant number to Alice. They broadcast this number. They say, look, anybody that wants to communicate with us, here's our number, here's that giant number that we have. I'm telling you now that this number is a product of two primes, just not telling you which two primes they are. Okay, to anyone that wants to communicate with Amazon. Alice gets the number, she combines, this is the brains behind RSA, she combines the number with her credit card number to get a new number. She sends the new number back to Amazon. Amazon receives the number, okay, and uses the secret factors. Amazon knows what these two numbers are, so they're going to use the large numbers, use the secret factors, those two numbers, to unlock the credit card number. Okay? Now, obviously, I'm leaving out the part of what does it mean to combine and what does it mean to unlock. That's the technical part of RSA, but that's basically the way it works. Grace, great. This is Alice and Amazon. Let's say there's an Eve. Eve for eavesdropper. Eve gets the large number and uses her quantum computer to find the factors. She takes this number. She uses Shor's algorithm to find the factors. Okay, and she gets her quantum computer to find out the factors. Then she can do the same thing. When Alice sends her credit card number, Eve eavesdrops and unlocks Alice's credit card number. So the minute somebody has a quantum computer that can factor large numbers, they can break anything. Okay, great. So this is telling you that when quantum computers are done, then RSA is done, and we're going to have to find something else. But don't get nervous. Okay? I'd like to show you why you shouldn't get nervous when we talk about the post-quantum world. You'll still be able to buy things over the Amazon. For example, if you want to buy this book on Amazon.com, you can still use it. There's no thing. Anyways, it's pretty cheap. It's very important. Okay, next. So I'd like to tell you something about why you shouldn't be nervous. Okay, and I have 10 minutes to do it. So it's something called the traveling salesman problem. I don't know if you've ever seen it. You ever seen it? Good. Good. A traveling salesman wants to visit some cities, and he wants to find the shortest path that hits every city exactly once. He wants to go to one city, sell his stuff, go to another city, sell his stuff. He doesn't want to go to the same city twice because he sold it, and he wants to come home. So here's a typical type of data that he'll have. New York, Miami, Los Angeles, Denver, Chicago, and he has all the numbers of the distances. And his goal in life is to find the shortest possible distance between them. What's the shortest way of making a route through all 6 of these cities to see what the shortest way is? Okay? A traveling exactly once. For 6 cities, he has to check 6 factorial. He has 6 possibilities for the first city, 5 possibilities for the second city, 4 possibilities for the third city. He has to check all these different possible ways of going around to all these cities. And that's not so bad. That's 720 possible paths. So he wants to find the shortest route. He has to go through all 720 possibilities and find the shortest route. No problem. How about for n cities? Not 6 cities, but n cities. By the way, this computer here can do about 1 million routes in a second. What does it have to do? For every route, it has to add up all the numbers, okay? What the path is, okay? Add up all the numbers, compare it to shortest so far, and see if it's shorter, and just keep on looking for the minimum. Not so hard. You can do it 1 million in a second. For n cities, it would take, he has to check n factorial possible paths. He has to say there's n possibilities for the first city, there's n minus 1 possibilities for the second city, etc., etc. So it could have something like this, okay? Or it might be something like this. Whatever you're trying to find, here's, I don't know, 30 different dots. He wants to visit all 30 of these cities. What's the shortest possible route? Okay, how about for 100 cities?
100 times 99 times
100 times 99, he would have to check 100 times 99 times 98 times 98. You know the song? 99, whatever. Question, how long would it take? Well, yeah, it depends how fast your computer. I'm telling you, this computer can check 1 million routes in a second. How long would it take?
It's more than a million.
Very long.
What's 100 factorial?
Okay, days. I can tell you, for 720, you would do this in less than a half a second. Less than a quarter of a second. Less than a thousand.
Millions noise.
Okay,
A very large number.
a very large number. How long?
A million years.
A million years. Anybody else?
Billion years.
Eat that
A
thing
million
first.
years. A billion years. Okay, anything else?
Has to eat that thing first.
More than 2 weeks? More than 2 weeks. Okay, let's check it out. Guess how long? Okay, let's calculate 100 factorial. Well, that's 100 factorial. So that's the amount of possible paths. Okay, you have to understand, when you multiply by 100, you're adding 2 digits. When you multiply by 99, you're pretty much adding 2 digits. When you multiply by 98, you're still adding 2 digits. So you're adding 2 digits every time you do it. Okay, but I'm not interested in how many paths. I want to know how long it would take this computer to figure it out. So this computer could do 1 million paths in a second. So it would take, divide that by 1 million. I get that. That's how many seconds it would take. Divide that by 60 to get how many minutes it would take. Divide that by 60 to get how many hours. Divide that by 24 to get how many days. Divide that by 365 to get how many years. It would take 2.9 times 10 to the 142 centuries to solve this problem. It's more than a couple of billion years. More than a couple of billion years. Okay? A lot more. Okay? This is an essential limitation of our ability to know. And by the way, it's a simple question. Traveling salesman problem. He wants to visit the 100 most populous cities in America. He wants to visit each city 3 days, sell his wares, move on to the next city. He wants to know what the shortest route is. It's a normal question. Okay? But it's an essential limitation to our ability to know. Hold on. If you want to know more about this, you have to buy this book. $16, Amazon.com. It's called The Outer Limits of Reason, What Science, Mathematics, and Logic Cannot Tell Us. By me. Okay, anyways, passing it around. What, you take
How
a
long-
picture of it and buy it.
How long would it take for the quantum computer to do like Tower of 9?
We'll deal with it. Oh, Tower, no, but we'll deal with this. Okay, so it will take 2.9 times 10 to the 142 centuries to solve this problem. Okay, great. Whenever I teach this, I get people say, big deal, I'm going to get a faster computer. This is a slow computer. And I can tell you now, in 20 years, this will be a slow computer. So in 20 years from now, this will be a slow computer. In fact, I promise you, in 20 years from now, computers will be going 10,000 times faster than they are now. I can tell you, I'm a little bit older than most of you, I can tell you computers go 10,000 times faster than when I was 20 years ago. Okay? Computers are going faster. So let's imagine for a second we have a computer that does 10,000 times faster than 1 million. What's that? That's 10 billion routes in a second. Let's see, Will that solve our problem? Okay, and the answer is yes. Then you'll only need, instead of 2.9 times 10 to the 142, you'll need 2.9 times 10 to the 137 centuries. That's 1/10,000th of the bigger number. So faster computers are not going to help you. Next, how about let's be very modern, let's put it up on the cloud and have everybody download an app that tries to do a bunch of things, and we'll have 10,000 people running their computers doing it all, da-da-da-da-da-da. See, I'm sounding modern, right? Okay? Anyways, that will only need, if you can do it 10,000 times quicker, that will only be 2.9 times 10 to the 137 centuries. It's not going to help. Okay, now you might say, okay, let's do it on 10,000 processors that are 10,000 times faster. Fine. So then it's 134 centuries. 10 to the 134 centuries. Not helping. Okay, physicists tell us that there are 10 to the 80 particles in the universe. If every particle in the universe was a computer then working on this particular problem of solving a 100-city traveling salesman problem, then you can only take, it will only take 10 to the 62 centuries. If every particle in the universe was working on this problem, it would only take 10 to the 62 centuries. Okay? Which means not every particle in the universe is working on your problems, but this problem is not going to be solved by many processors. Okay? What about quantum computers? Okay, that's the whole reason why I bring this up, quantum computers. Well, quantum computers can help. It would do it, you could do Grover's algorithm, it would take 10 to the 71 centuries to do it. That's the square root of 10 to the square root of 10 to the 142 is 10 to the 71 centuries. That's not going to help you either. Okay? My point here is that there are a lot of other hard computer problems that quantum computers cannot deal with that will still give you security. So don't worry, oh, you know, as soon as RSA is busted, we're not going to have anything. No, RSA will be busted, I promise you. In a couple of years, we'll have massive quantum computers. But there will always be harder computer problems that cannot be solved by quantum things. So don't be worried about it. Main point, there are very hard problems even for quantum computers, so there will always be quantum security. Okay, just a little bit, I'm finishing in 5.
One question, they have to be, the problems have to be easy to create and hard to solve, right? Like factoring.
Right.
So what's the easy way to create a TSP problem that's hard to solve?
I don't know. There are people working on it. It's called post-quantum cryptography. There's a whole thing of it. But the point is, traveling salesman is what's called an NP-complete problem. Factoring is not an NP-complete problem. As long as we have NP-complete problems, which are very, very hard problems, even a quantum computer won't help them. There are... Okay, the height. Okay, this is the speculative part of the talk. This is not technical. I just want to say, every major country is fighting, all these major countries are fighting over quantum computing. And they're trying to be the first. IBM, Microsoft, Google, all these companies are fighting over this. And there was a big thing recently, Google came out and said that they have a problem, they did quantum supremacy, which means they have a problem that a quantum computer solved that would take 10,000 years for a classical computer to solve. This is like 3 weeks ago. It was the front page of the page. And it would take 10,000 years for a classical computer to solve this problem. And IBM came out the next day and said, yeah, we can do it in a couple of days with a classical computer. That's not really a problem. They were like, you didn't get supremacy yet. Okay, but again, they're fighting over who will get supremacy, but the point is, there's a lot of money involved in this. There's a lot of people putting out money in this. These are, I just went to, downloaded all the universities that have quantum algorithm, quantum computing things. You can't even read it. Oxford, Purdue University, all of them have labs doing quantum computing. Okay. The Dutch had this concept of tulip mania. It's worth looking into. Read the Wikipedia page. But a lot of these things are there's a lot of hype to this. It's not necessarily going to change your life. Quantum computers are fascinating things, worth buying the book and reading the book. and taking a class in it, et cetera, but to imagine that it's gonna change the world as much as it's supposed to be changing the world is a little bit too much. There's a lot of ways to quantify success, number of qubits, largest number factored. All these companies and all these countries are saying, look, we factored, oh, this is what I was telling you. About 10 years ago, IBM said they implemented Shor's algorithm. Remember Shor's algorithm was how to factor numbers? And they had a 5-qubit quantum computer, and they plugged in the number 15. 15, you can all figure out what the 15 is. And they let the quantum computer run, and it came to the conclusion that 15 is equal to 3 times 5. They factored 15. Okay, that was 10 years ago. There was a lot of excitement at the time. The point is they want to show so that numbers can be factored. Anyways, there's different hardware. There's a lot of money involved. Investors, banks are interested. It's more about the investment than the computing power. They're fighting with each other to try to overcome it. Think of how the world has changed. Okay, I don't want to do that. Has your life really changed because computers are faster? Hold on. Summing up. Quantum computers use superposition and entanglement to solve problems more efficiently than regular computers. There's a formidable physics engineering challenge to create large-scale quantum computers. You have to keep them isolated. They will probably get there, and when they do, RSA will be useless. But there are other harder problems than factoring that will be used to get computational security. It is not clear that quantum computers are really going to change the world. The future is unfathomable. That's what makes this topic so fascinating. Thank you. Okay, I just want to point out, I wrote this article, Professor Novak Xerox about 10 copies of this. It's an article called An Introduction to Quantum Computing. Okay, it's a 30-page article, very, very basic. But and if you can't get it here, you can get it on my webpage. So you can download it if there's not enough people here. Okay, and then this book is Quantum Computers for Computer Scientists. It's the rest of the books are, you have to have a physics background. Every chapter is a different title of a computer class. Architecture, don't move. Algorithms, programming languages, theoretical computer science, cryptography, information theory, hardware, et cetera. Okay? And these two books, Programming the Universe, A Quantum Computer Takes on the Cosmos, those are two popular science books about these things that are very readable. And that's it. Thank you very much. I'm not running, you might know, right, from years ago. Yeah. I'm not running anywhere, and it's a pleasure talking to you. I'm just going to shut the computer.
Push it.
Yeah, I did.
Are they trying to